In the realm of facial analysis, understanding and recognizing facial expressions and action units (AUS) has garnered significant interest in the computer vision community. Recent studies have proposed various deep learning-based approaches to achieve state-of-the-art performance in facial expression recognition (FAIR) and O recognition (AUR). However, constructing effective positive-negative pairs for contrastive learning on facial behavior datasets remains challenging due to the subject ID information and limited number of subjects in these datasets. To address this issue, the authors propose a text-driven contrastive learning method, called CLEF, which utilizes both coarse-grained information and text-embedded labels. The proposed method comprises two stages, both using a unified vision text architecture known as CLEP. In pre-training, for each anchor in a batch, positive samples are from the same activity, and negative samples are from different activities. The activity descriptions are used as coarse-grained labels to guide the Weakly-Supervised contrastive learning model, aiming to minimize the intra-activity differences in representations. The authors leverage activity descriptions to create positive-negative pairs, increasing the possibility of grouping images with the same expression into positive ones and encouraging the encoder to focus on activity features rather than identity features. Cross-modal contrastive learning is designed to push image features close to textual features, enhancing the learning of better representations and improving the performance of FAIR or AUR in downstream tasks. In fine-tuning, the authors apply vision text contrastive learning directly to classification tasks. Supervised contrastive learning adapts the image representation to be close to its corresponding label name feature, while self-supervised contrastive loss encourages the feature of label names and descriptions to be similar, enriching the semantic information of the label representation. The recognition prediction is based on finding the most similar label names of the testing image, following the method used in CLEP. The main contributions of this paper include proposing a weakly-supervised contrastive learning method that effectively leverages coarse-grained activity information, exploring the use of text-driven contrastive learning on FAIR and AUR tasks, and conducting extensive experiments on 3 in the lab and 3 in the wild datasets. The proposed CLEF model leverages contrastive learning to enhance facial behavior recognition, utilizing both image and text modalities. It consists of 2 stages: pre-training and fine-tuning. In pre-training, the model aims to learn robust deep representations and alleviate the influence of identity variation. This is achieved through a cross-modal supervised contrastive loss that pulls together features from the same activity and pushes away features of other activities. The loss function includes terms for image-image and image-text pairs, encouraging similar representations for images and their corresponding texts. In fine-tuning, the model adapts to both image and text scenarios, utilizing the image and text encoders. The loss functions include self-supervised contrastive loss for name description pairs and supervised contrastive loss for image label pairs. The self-supervised contrastive loss is designed to enhance the similarity between name and description features, while the supervised contrastive loss encourages similar representations between images and labels. The proposed CLEF model has been evaluated on 6 datasets, achieving state-of-the-art performance in all of them. This demonstrates the effectiveness of the proposed method in enhancing facial behavior recognition. The model's ability to leverage textual information in addition to visual data sets it apart from previous works, which only utilized image encoders in downstream facial analysis tasks. The proposed contrastive learning for emotion and facial action unit recognition (CLEF) method jointly trains supervised contrastive losses for image-text pairs. The loss functions for facial emotion recognition (FAIR) and action unit recognition (AUR) are defined as LFE and LAO, respectively. LFE is a multi-class classification problem, while LAO is a multi-label problem. The total loss function in fine-tuning is a combination of the supervised contrastive loss and the self-supervised contrastive loss, defined as Lfine equals lambda L alpha plus LDN 2.0. The method also utilizes prompt templates to augment the original label, similar to CLEP. The prompt templates are used to generate multiple textual representations for label names and descriptions. The model architecture consists of a text encoder and an image encoder, where the text encoder is a 12-layer transformer and the image encoder is a VITB16 model. The model is pre-trained on BP4D and BP4D plus datasets using weakly-supervised contrastive learning, and then fine-tuned on downstream tasks. The implementation details include a batch size of 64, ADAMF optimizer, and cosine decay with a minimal learning rate of 1/6. The evaluation metric for AUR is the averaged F1 score over all AUS, and for FAIR it is accuracy. The proposed method is compared with several state-of-the-art works on BP4D and DISFA datasets. The results show that CLEF achieves the best performance on both datasets, with an F1 score of 65.9 on BP4D and 64.8 on DISFA. The method also outperforms other state-of-the-art works on EffectNet, RAFDB, and FAIR plus datasets. The results are presented in tables 2 and 3, which show the F1 scores in terms of 12 AUS on BP4D and 8 AUS on DISFA, respectively. The bold numbers indicate the best performance, and the bracketed numbers indicate the second best. The proposed method achieves the best performance on both datasets, demonstrating its effectiveness in facial action unit recognition and facial emotion recognition. Here is a combined summary of the 2 pages. The authors present the results of their proposed method, CLEF, on the BP4D Plus database, achieving outstanding performance and outperforming state-of-the-art methods in 3 AUs, namely AU4, AU23, and AU24. The overall improvement is 1.4% compared to the baseline methods. Additionally, CLEF achieves the best performance on average F1 score in terms of 8 AUS on the DISFA database. The authors also demonstrate the generalization ability of CLEF on the facial expression recognition task, evaluating its performance on 3 commonly used in the wild FAIR databases. CLEF achieves the best performance on EffectNet 7, RAFDB, and FAIR+, and slightly lower than DMUE on EffectNet 8. In the zero-shot evaluation, CLEF is trained with neutral, happiness, and fear on EffectNet and tested on sadness, surprise, disgust, and anger on RAFDB and FAIR+. The results show that CLEF outperforms the baseline FARL obviously. The authors conduct an ablation study to evaluate the effectiveness of each component in CLEF, including pre-trained stage with images, pre-trained stage with activity texts, image encoder, label names, and label descriptions. The results show that using both names and descriptions achieves the best performance, demonstrating an optimal balance between distinction and similarity. The authors also visualize the expression features extracted by the baseline method and CLEF on RAFDB, showing that CLEF effectively enhances the separability of different classes. Furthermore, they visualize the similarity matrix and correlation coefficient matrix of the text features on RAFDB, as well as the relevancy between the image and corresponding text queries using GAI. The paper presents a weakly-supervised text-driven contrastive method for learning advanced facial representations. The approach leverages coarse-grained activity information to disentangle the effects of subject identity features and minimize interactivity feature differences while maximizing interactivity feature differences. The method incorporates textual label names and descriptions to directly apply to facial expression recognition, FAIR, and facial action unit recognition, AUR, tasks. The authors visualize the relevancy heat map between image name and image description pairs using a graph autoencoder, GAI, demonstrating that the text encoder successfully learns to extract semantic knowledge even from label names. The heat map localizes the corresponding regions of the face by querying the label name or label description. The paper discusses the advanced pairing method, which is activity-based and designed to elicit specific expressions, resulting in images with expression intensity ranging from none to onset, peak, and offset. The authors also highlight the easy extension of the method by integrating intensity details into label names. However, the authors acknowledge limitations, including the reliance on prior knowledge of coarse-grained textual descriptions, the use of a fixed prompt template for label names, and variations in performance across AUS caused by semantic descriptive writing. The proposed method, CLEF, achieves state-of-the-art results on 3 widely used in the lab databases for AUR and 3 in the wild databases for FAIR. Ablation experiments demonstrate the effectiveness of weakly-supervised contrast learning in pre-training and the validity of using textual information from activity, label name, and label description. The paper provides a comprehensive overview of related work in facial expression recognition and action unit recognition, citing various studies that have contributed to the advancement of these fields. The referenced papers present various approaches to facial action unit detection, facial expression recognition, and related tasks. Several studies focus on developing novel architectures and techniques to improve performance in these areas. For instance, 26 proposes EAC-NET, a region-based deep enhancing and cropping approach for facial action unit detection, while 27 introduces a self-diversified multi-channel attention mechanism for facial action analysis. Other works, such as 28, 34, and 43, explore the use of attention mechanisms, transformers, and visual linguistic representations for facial expression recognition. 28 investigates internal diversification for redundant attention in generic facial action analysis, while 34 utilizes visual transformers and attentional selective fusion for facial expression recognition. 43 revisits self-supervised contrastive learning for facial expression recognition, demonstrating its effectiveness. Some papers emphasize the importance of uncertainty estimation and handling in facial expression recognition. 44 proposes uncertain graph neural networks for facial action unit detection, while 45 and 47 introduce hybrid message passing with performance-driven structures and pixel-interested and anti-person-specific facial action unit detection net with discrete feedback learning, respectively. Several studies also focus on developing novel datasets and evaluation protocols for facial action unit detection and facial expression recognition. 36 presents the DISFA database, a spontaneous facial action intensity database, while 38 introduces the EffectNet database for facial expression, valence, and arousal computing in the wild. Furthermore, 49 and 50 discuss the use of attention mechanisms and neural image caption generators for facial expression recognition. 52 proposes region attention networks for pose and occlusion robust facial expression recognition, while 54 introduces de-expression residue learning for facial expression recognition. Overall, these papers demonstrate the diversity of approaches and techniques being explored in the field of facial action unit detection and facial expression recognition, highlighting the importance of attention mechanisms, uncertainty estimation, and novel architectures in achieving state-of-the-art performance. The supplementary material provides detailed descriptions of the activities and label semantics used in the Weakly-Supervised text-driven contrastive learning for facial behavior understanding framework. The activities in the BP4D and BP4D Plus datasets are described in tables 1 and 2, respectively. These activities are designed to elicit various emotions, such as happiness, sadness, surprise, and fear. The label semantic descriptions are based on psychology studies and are divided into two categories: facial expression and facial action units, AUS. The facial expression labels, including anger, contempt, disgust, fear, happiness, neutral, sadness, and surprise, are described in detail, highlighting the characteristic facial features associated with each emotion. The facial action unit labels, on the other hand, describe specific muscle movements and their corresponding facial features. The descriptions are based on the work of Sev. 4, and psychology studies. 2. The labels, including O1 to AU26, are described in detail, covering various facial features, such as eyebrow movements, cheek raisers, and lip tighteners. The pseudocodes for pre-training and fine-tuning are provided in Algorithm 1 and 2, respectively. These algorithms outline the steps for training the model using the text-driven contrastive learning framework. Text prompt templates are used to generate label name and description prompts. The label name prompts use a single template, a photo of a person with N, where N represents the label name. The label description prompts use one of 7 templates, which are randomly chosen to generate a prompt. These templates include phrases such as, a photo of a person with D, or, a photo shows a person that D, where D represents the label description. Overall, the supplementary material provides a comprehensive description of the activities, label semantics, and pseudocodes used in the Weakly-Supervised text-driven contrastive learning for facial behavior understanding framework. Here is a combined summary of the 2 pages. The authors present the Contrastive Learning Framework for Emotion and Facial Action Unit Recognition, CLEF, which consists of two stages: pre-training and fine-tuning. In the pre-training stage, the model learns to extract feature representations from images and text descriptions using vision and text transformers, respectively. The authors defined two types of feature representations: image, I_F1 and I_F2, and image text, A_F. They then calculate scaled cosine similarities between these feature representations, resulting in logit_e and logit_it. The supervised contrastive loss function is applied to these logits, and the total loss is the average of the two losses. The authors also provide templates for expression labels, activity descriptions, and label descriptions. These templates are used to generate text descriptions for the images, which are then used as input to the text transformer. In the fine-tuning stage, the model is trained on a specific task, such as facial expression recognition, FAIR, or action unit recognition, AUR. The authors defined three types of feature representations: image, I_F, label name, N_F, and label description, D_F. They calculate scaled cosine similarities between these feature representations, resulting in logit_in and logit_dn. The loss function is a combination of the task-specific loss, cross-entropy loss for FAIR and binary cross-entropy loss for AUR, and the loss from the label description. The authors provide implementation details for fine-tuning and pre-training, including hyperparameters, batch sizes, and augmentation strategies. They also conduct an ablation study on the hyperparameter lambda, which controls the weight of the loss from image name pairs, and find that the performance reaches its peak when lambda is set to 2. Finally, they provide visualizations of the prediction probabilities on the RAFDB dataset, showing both successful and failed predictions. The authors draw upon a rich body of research in facial expression analysis, citing seminal works by Ekman and Friesen, 1971, and Ekman and Rosenberg, 1997, which introduced the facial action coding system, FACS, for categorizing facial movements into action units, AUS. Matsumoto's 1992 study provided further evidence for the universality of contempt expressions. Building upon these foundations, the authors leverage recent advances in computer vision and machine learning, specifically referencing Yang et al.'s 2021 approach that combines semantic embedding and visual features for facial action unit detection. This work serves as a cornerstone for the proposed methodology, which aims to improve the accuracy and robustness of O detection. The authors propose a novel framework that integrates multimodal features, including visual, audio, and textual inputs, to enhance the detection of subtle facial expressions. This multimodal approach is motivated by the understanding that facial expressions are often accompanied by corresponding audio and linguistic cues. The framework comprises two primary components: a visual feature extractor and a multimodal fusion module. The visual feature extractor employs a convolutional neural network, CNN, to extract spatial and temporal features from facial images. The multimodal fusion module integrates these visual features with audio and textual inputs using a graph attention mechanism, which captures the relationships between different modalities. The authors also provide an overview of the dataset used for training and evaluation, which consists of annotated facial expressions with corresponding audio and textual labels. The dataset is designed to capture a wide range of facial expressions, including subtle and complex emotions.